Hi, I'm Bill Morrison. We design and build BIGS loudspeaker systems. I think there's a label up here, and there's probably a label up on that speaker as well. But you need BIGS systems because you need systems that will play at high sound pressure levels and will play cleanly with phase accurate and frequency response accuracy. It's important if you're going to have accurate monitoring systems to allow you to listen through the full detail of all the mix that you have and through its full dynamic range. It's important to have a listening room that doesn't really destroy that accuracy by introducing reflections and noise and resonances of its own, which would interfere with the first arrival signal from the speaker. And so I wanted to go into what's necessary to create a perfect listening room, which would also apply for a control room in a recording studio situation as well. A couple articles I want to refer to. One of them is an article by Tom Hidley. Tom Hidley is the highest paid designer in the world. He wrote an article entitled "Make a Room Sing for $3,500." And although it probably costs a lot more than that now, but there are a lot of important information in there. Also, I wrote a couple articles for Mix magazine on using room geometry to achieve an accurate monitoring environment. And we'll go into that. There's also a couple software programs that are helpful. One of them is REW, which besides having some FFT type programs in it that really let you analyze your monitoring system accuracy and the acoustical conditions within your room, allowing you to analyze reflections and the level of reflections and what interference problems you may be having. It also has a section in there called Room Simulator, which lets you look at various dimensions of listening rooms, different acoustical treatments within the room, various loudspeaker positions and listening positions, and see how all those interact with each other and affect monitoring accuracy. The other program is EASE, which is Electroacoustic Simulator, and it allows you to really look at more complex situations in greater detail. So you can put in various room shapes and different acoustical treatments on different portions of the room. It also has an interesting feature that allows you to put in a waveform file so you can actually listen to what music or some acoustical source would actually sound like within the room. So I recommend it. It's a little bit more complicated to use than the room simulator, but still, very useful. As far as achieving a perfect listening room, there are basically three things that you really want to achieve. One of them is unless you're in an open field, which would be a great situation as long as there's no wind and any environmental problems. Unless you're in an open field, you need to have some kind of shell around you to form this room. And this shell, I'm just going to draw a rectangular one here just for illustration. It has to be basically rigid and non-resonant. So the walls need to be of heavy construction, hopefully concrete. The floor needs to be of heavy construction, hopefully concrete. And the ceiling needs to be of heavy construction. There aren't a lot of concrete ceilings, but you can have heavy construction in the ceiling to achieve the same results. So on the floor, if you don't have a concrete floor, then you may want to pour a concrete floor. You may want to add additional weight to the floor, tile, or additional hardwoods to the floor would add some extra weight and solidity to the floor, which would definitely help that situation. Then for the walls, if they're not concrete walls, then they may be gypsum on stud walls. you may need to add some additional layers of type X gypsum that are, each layer needs to be staggered, taped, and sealed. And you may also introduce some soundboard between layers to actually dampen resonances within those materials. So multi-layer of gypsum on the walls is a good thing, and is used in typical construction of perfect listening rooms. Same thing is true of the ceiling. You may need to add additional gypsum layers to the ceiling to solidify it. If it's going to be a weight problem, then you're going to have a iron grid that actually supports the gypsum layers in the ceiling. So once you've achieved this solid shell around your listening room, let's put this down here, a solid shell, and SHELL, and non-resonant. Then you need to also now make sure that you don't have detrimental reflections that are going to molest or interfere with the first arrival from your speaker system. So in your listening room, typically you would have a couple of speakers in here, and they need to be symmetrically placed in the room, facing the long dimension of the room, hopefully. And then you would position these with respect to the listening position in an equilateral triangle, so the distance between the speakers is the same as the distance from the speaker to the listening position. And there is one specific listening position that is really optimum. There's no way you can avoid that. You need to be equidistant from each of the speakers, and you need to make sure that the system, hopefully your system is a time accurate system and has coincident arrival from the components within the system. There's really only one position where those drivers are actually arriving in correct time alignment. So based on the requirements for correct time alignment and being equidistant from the speakers, you're basically in a fairly small listening area where you can actually achieve perfect listening to really hear what's going on accurately within the mix. So anyway, you then have to analyze what's going on with reflections in the room that are going to cause these problems with really listening to the first arrival or hearing the first arrival accurately. And the sidewall is a reflection problem, of course. So if you analyze the sound that's radiating from the speaker coming to the sidewall, it would bounce back into the listening position. This is just one path. There are many other paths that would also bounce back. But just for illustration, I'll just show this one path here as a reflection back to the listening position. You would need to make sure that this is absorbative in this area here to eliminate this reflection. And when I say eliminate the reflection, I mean that it needs to be reduced at least by 20 dB with respect to the amplitude of the first arrival that is arriving to the listener's position. So if you can attenuate this by 20 dB, you will achieve a perfect listening environment. Obviously, if you can achieve greater attenuation than that, that's an improvement. And that's why I say, an open field would be a great thing, because there would really be no reflection coming back. It would be sort of an anechoic type environment. Excuse me. A lot of people think that if you have speakers in an anechoic type environment where there are no reflections, they're going to sound dead. But the opposite is true, because you can really hear the detail and all the spatial information which is in the mix. And so they sound amazing. However, there are some recordings that are actually recorded in, and these are very few recordings, that are actually recorded in an anechoic environment themselves. So they really rely on the system that you're listening to create reflections that would make it, sound natural. But those are very rare, specialized recordings that nobody really listens to. But anyway, so you need to control these reflections. If you actually analyze what's going on beyond where the listening position is, you'll see that reflections beyond that are actually not going back to the listening position. They're actually reflecting back to the back wall. And that's where you need to have absorbers on the back wall to control that reflection. In Tom Hidley's article, for absorption, he recommends hanging 4 by 8 sheets of half-inch particle board from the ceiling to the floor, but leaving a gap of a couple inches from the top of the ceiling and a couple inches to the floor. So it's sort of like freely suspended panels. And then each panel he would put, in his article, he specifies half-inch fibrous absorption on the face of this panel that faces the room. However, I'd probably recommend a couple inches as being better. But in his article, he actually recommends joining all these panels together and going all the way around the room with these panels. I don't really think you need to go all the way around the room, because I explained the reflections beyond where the listening position is actually go back to the back wall, and it's not really important to have this area here as being absorbative. So in addition to these wall reflections that you have to be concerned about, of course, there's the front wall, which is also a problem. Speakers basically are omnidirectional unless you have some dipole type speakers or Diopolodo speakers. But basically, for a lot of the frequency ranges that in the audio spectrum, the speakers can be considered omnidirectional for really analyzing what's going on and how to create a perfect room. So a lot of the sound energy will actually come off this front wall here and bounce back into the engineer's or the listening position and cause a problem. So it's important to make sure this is absorbative on the front wall. If you do have to have a door or some big screen or something on this front wall, it's really better to bring this front wall out and put it between, so it spans between the speaker systems. And if you really analyze this, you'll see there's no reflection path that gets back to the listening position if you have this this front area spanning between the two speaker systems. Another way to control reflections off the walls, and for that matter the ceiling and the ceiling as well, is you can actually angle these walls. So if you angle, say for instance you angled this wall here like this, you would see that the reflection from the speaker system would actually be diverted back to the back wall. If this angle is correct, you have to make sure the angles are correct, of course. And they're really dictated by the reflection law, where the angle of incidence is the angle of reflection. So if you can angle this wall here and reflect the energy back to the back wall where it's absorbed, then this wall here can actually be reflective. So you could actually have a door or a window or something like that in those angled sections. If this is taking up too much space or requiring too much real estate for you to create these angle walls here, you can actually break up these into sections. And I think I'll show a picture of a listening room that shows these staggered wall sections here. It's a system we designed. Well, we designed several systems like that, but this was for a studio in Florida. So by using geometry here, you can also control these reflections. The same thing is true on the ceiling. Of course, if you look at a section through this perfect listening room, you'll have the listener here and you'll have a speaker here, and you'll see that there's a reflection off of the ceiling that's going to interfere with this first arrival from the speaker system. And so you need to suspend a cloud above this area, and usually like 6 inches below the ceiling, and there will be diaphragmatic absorbers and fibrous absorbers within this cloud. There may be also some special little lights or something in there to make it look great, but it's important to have this, or you can actually angle this ceiling up. If you want to construct the room that way, you'll find that you can construct this so that the angle is splayed upwards such that the reflected signal does not actually go to the engineer's position. It actually goes to the rear wall, where you can have absorption, diaphragmatic and fibrous absorption on the back wall. The same problem exists on the floor. There's going to be a reflection off the floor, so you actually need an absorber on the floor here. In the case of a recording studio or something, usually there'll be like a console here, so you can put an absorber on the face of the console to control that reflection. So anyway, that's really the way to control reflections in your perfect listening room. You just want to make sure that your first arrival is not being tampered with or interfered with by reflections. And the third aspect is the noise floor in the room needs to be reduced. So basically, the ambient noise levels in the room from environmental or adjacent environmental problems or from the HVAC system needs to be reduced to what's called NC20 sound levels. And this is basically a criteria that the heating and air conditioning industry mechanical engineers have developed to specify systems that do not exceed these NC20 levels. So there are various conditions for the duct system design. Obviously, you need to have a certain volumetric velocity for the heat load that's in the room, but the linear air velocity of the ducts themselves, the air within the ducts, needs to be below about 300 feet per minute to prevent turbulence from the air from introducing noise levels in the room that would be unacceptable. So basically you're just dumping slow air into the room and extracting slow air into the room. Additionally, the duct systems need to be heavy walled duct systems with lined internally with line acoustic. They need to extend for some length and have some 90-degree turns in them to really eliminate noise from the air handling unit, and also to prevent sound from traveling from, say, areas that are serviced by the air conditioning system that might be adjacent to your listening room. So anyway, basically, once you've achieved the solid non-resonant shell for your listening room, and you control the reflections so you don't have, so that you actually hear accurately the first arrival from the speaker system, and you have a low noise level in it, you should have a perfect listening room. Of course, cosmetic concerns are something that we're really not going to address here, but it's important for it to look nice as well. And I'll show some photographs of what I consider nice looking listening rooms.